乘以派 n 为坤线。
是关注。
Greetings, honorable judges, worthy opponents. This is the team leader of 物理探花 from Typt Senior High School, and I'm Yu Fan. And these are my teammates Yu Shen, Yu Yihui, Li Tingyu, and Xu Kai. Thank you.
So I'm the team leader of Team Fibers, and I'm Liu Yan.
Okay.
Thank you very much.
Okay, so the first part, the opponent challenge.
Okay, so we would like to challenge problem number 1, the fractal finger.
We accept the challenge.
Okay. Yeah, so please write your name and your fractal. can start.
Hello, notable juries and fellow competitors. I am the reporter from Team Excel here, and what I'm going to report today is problem number 1, fractal fingers. And here's the problem statement. The effect of fractal fingering can be observed if a droplet of an ink alcohol mixture is deposited onto a diluted acrylic paint. How the geometry and dynamics of the fingers are influenced by relevant parameters. And I will mainly focus on the formation of fingers and how the geometry and dynamics of the fingers are influenced by relevant parameters, such as the initial concentration variation and the volume of the mixture. And this is the outline of my report. First, I'm going to, in the preliminary experiment part, I will show the observation video and explain this phenomenon. And in the theory part, I will show the theory to calculate the characteristic radius. And in the experiment part, first I will show, introduce my setup and the measurement of the boundary condition of this phenomenon, and I will do the experiment like parameters like initial concentration and volume of the mixture, and also the height of which is the thickness of the diluted acrylic paint. And finally, I'll give a conclusion. And preliminary experiment part. This is the option. And this is the observation video. And you can see that when with a lower concentration of alcohol, the mixture will not formate fingers. But with a higher concentration, which is a medium concentration, you can see that the finger clearly. But with a too high concentration of alcohol, you cannot observe finger clearly because the alcohol evaporates really fast. So we can know that this phenomenon is mostly influenced by the concentration of a mixture. And next is about the phenomenon explanation. First is the gravitational effect. You can see that the drop will flatten because that gravitational force will pull it so that it gets flattened. And you can see that the inner part of the mixture is thicker and the rim part will be thinner. And so that the thickness difference will cause the evaporation differences, so that in the inner part of the mixture, the concentration of the alcohol will be higher, and the concentration at the rim will be much lower. And the concentration difference will cause the surface tension difference. And because the surface tension of the alcohol is lower than the ink, so that the net force will be triggered from the lower surface tension area to the higher surface tension area, which creates the Marangoni flow, which is the main cause of the expansion of the mixture. And next is about the surface energy between different interfaces. Because that the system will tend to minimize the surface energy, so that when the surface tension between the air ink interface is smaller than the diluted acrylic paint and the air interface. Increasing the interface area can reduce the surface energy. So that is called the expansion. And after the mixture evaporates, the concentration will be much lower, so that the surface tension will be higher. The surface tension of the mixture will be higher, so that the surface tension gradient will not be able enough to trigger the strong Marangoni flow, so that it spreads lower. And so finally it will stop at the maximum radius. And next is about the formation of fingers. And since that the system will tend to minimize the surface energy, so that it will reduce its surface area. And because of probabilistic contributions, some of the places in the boundary of the mixture will want to decrease its surface area, so that it forms a fingering boundary. And this is the boundary of the finger. And since that the Marangoni flow will pull the finger outward, so that the finger will expand. And the finger will, in the boundary of the finger, it will split into the two parts of the finger because of the probabilistic contribution. And next is about the influence of the surfactant and viscosity. And since that both the acrylic ink and the diluted acrylic paint, they are both a surfactant, so that they interface each other, so that they can flow with each other. And since then, also the interface between the mixture and the diluted acrylic paint, they will blend together. So and also the viscosity of the diluted acrylic is really high, so that the viscous force will influence this phenomenon. And then the finger won't fragment to a small droplet because of the viscosity, viscous stress hold it, but it slowed down since the Marangoni flow declined. And next is about the theory. We can calculate the variation of the surface tension by deducting the surface tension when the alcohol is in the critical concentration minus the minus the surface tension when the critical concentration minus the surface tension when it is in the initial concentration, and we can get the surface tension gradient by dividing it with the characteristic radius. And due to our literature survey, we get the characteristic radius as this. And we also know that the characteristic radius will be proportional to the maximum radius. And also here we will define the maximum radius as the critical radius that the mixture will stop expanding. And here's the experiment part. Here's the experimental equipment that I use when I'm doing the experiment. First, I use a fluid medium to get the diluted acrylic paint, and I mix the acrylic ink and the IPA alcohol and to get a different concentration of the ink alcohol mixture. And I use a syringe to control the initial volume of the mixture. And I use a heating plate to control the temperature in order to control the viscosity of the diluted acrylic paint. And I use a plastic board to avoid environmental distributions. And this is what I'm going to analyze in my experiment. I will analyze the maximum radius and the finger's length of with the initial concentration of the mixture, initial volume of the mixture, and which is the thickness of the diluted acrylic paint. And this is what I'm going to measure. This is the radius what I'm going to measure, and this is the length of the finger what I'm going to measure in the experiment part. And here's what I measured about the boundary condition of this experiment. And I found out that after I measured it with the mass fraction and the initial volume and the mass fraction and the height of the diluted acrylic paint. And I found that only the initial concentration of the ink alcohol mixture will be a boundary condition of the experiment. So it's approximately 0.12. And this is the experiment about the initial concentration variation. As you can see in the graph, when the concentration of the alcohol is higher, you can see that it will get flattened later. And it's because that when the concentration increases, the mixture it will need more time to evaporate to a critical concentration. So with the higher concentration, it will have more time to expand, so that the maximum radius will increase. And this is the temporal evolution of the finger's length with the various concentration. And you can see that it has a negative correlation with the initial concentration of the alcohol. And it's because that the volume of the mixture is limited, so that the radius, when the radius is larger, the volume content in the radius part will be more than the finger part, so that the finger is smaller when the concentration increases. And this is about the initial volume of the mixture. And you can see that you can see that the peak will get flattened because that the larger volume will need more time to evaporate, so it will have more time to expand also, so that the maximum radius will increase. And in the initial volume in the temporal evolution of finger part, because that when the volume increases, the redundant volume it will be added onto the thickness of rim, so that the volume on the rim will be much higher, so that you can see that the length of the finger will increase. And next is about the experiment of the thickness of the diluted acrylic paint. You can see that the growth of the radius will slow down earlier with higher acrylic paint. And it is because that both of the mixture and the acrylic paint, they are both a surfactant. So the Mangoni flow will trigger the boundary layer to flow with each other. And because that we need energy to compensate the boundary layer, so that it generates a pipe flow. And with a thinner acrylic paint, it will need to move faster to compensate the boundary layer. But since that the energy is limited, so that the flux of the paint will decrease when the thickness of acrylic paint decreases, and so that the mixture will evaporate before the mixture expands outward to a greater extent. So the maximum radius will decrease when the thickness of acrylic paint decreases. And next is about the experiment about the temporal evolution of the fingers with various paint height. And as we know that in the previous page, the height of the arctic plane will increase, so that the flux will increase, and so that the maximum radius will increase. But when the maximum radius increase, more volume will be in the inside part of the mixture, so that the volume of the mixture is limited, so that the length of the finger will decrease. And next is about the temporal evolution comparison between the finger and the radius. As you can see, the finger will expand longer than the radius do, because that when the concentration is the same, because that when we drop the mixture onto the diluted arctic planes, the boundary will be influenced by the surface tension, so that it will pulls the boundary of the finger like this, so that it forms an ultra-thin region. And because the evaporation differences of the thickness of the mixture, so that in the ultra-thin region part, it will evaporate to a critical concentration earlier, so that the radius will expand, it will have less time to expand than the finger. And next is finally is the conclusion. First, we know that the mixture will be flatter because of the gravitational effect, and the thickness differences will cause the evaporation difference, and it will cause the concentration gradient, and the concentration gradient will cause the surface tension gradient, which triggers the magnetism, which is the main reason that the mixture expands. And also the finger will be formed by the difference of surface energy and the probabilistic distributions. And the finger will expand instead of splitting because the distance will hold it. And the initial concentration will have a positive correlation with the maximum radius. And the initial volume will have a positive correlation with the length of finger. And this is the end of my report.
Okay.
Okay, so going to report, I would like to ask some questions. So first, what's the main parameters of your experiment?
The initial concentration of the mixture and the volume and the thickness of the arctic plane.
Okay, thank you. Next one. So how do you define a finger in when you're observing? I will do the definition.
Please turn to page 16. It's here. This one. You can see that here you can see that clear. You can see a clear radius at the rim of the.
Oh, okay, I got it. So, in page 11, so will the inertia force influence the results?
Can you say repeat your question?
Inertia force. Will the inertia force
What do you
influence?
mean inertia force?
Inertia force influence.
Inertia force. What do you mean?
So you say you talk about the vicious force. So
Oh.
will the inertia force?
Oh, I mean the viscous force will hold the mixture from prevent it from it.
Yeah, but you know that when there is a velocity, there must be some inertia force,
Huh?
right? Inertia force. Do you know what is inertia?
What do you mean inertia?
Well, you talk
Inertia.
about the vicious force will
Yes.
hold it. So will the inertia force influence the
Inertia. Inertia.
inertia?
I don't know what is that. I don't know what do you mean.
Oh, okay. So we'll just skip. Why do you use isopropanol alcohol? Why don't you
Because
use Why don't you use ethanol or?
Both will talk about the evaporation of the isopropyl alcohol is higher evaporation rate.
Oh, okay. So did you try other alcohol like ethanol or butanol?
No, but I believe that we can observe the same phenomenon. if we
Okay.
use that.
Thank you.
Okay, hands up. Okay, opponent, please start.
Okay, so I'm the opponent from Team Fibrous, and today's the fractal finger. So this is the problem statement. The key point is that in alcohol mixture, diluted acrylic is the condition to form the finger, and while the target we're going to find is the geometry and dynamics of fingers. So in the observation video, the reporter just have different concentration of alcohol and states that concentration is the parameters, which clearly shows the phenomenon. It's just great, no comments. And in the parameters discussion, the reporter just show different concentration of alcohol, the volume, and the thickness. So which explain here about lack of parameters discussion. Okay, in the theory part, the reporter just say about the gravity, which we think is a very great explanation of this theory, and they define a characteristic radius, which is also very good. But the reporter just skipping the page just too fast, so we will ask you later. And lack of explanation, the back explanation of theory. And in the experiment part, reporter just temporal evolution comparison. Now, the pros is that the setup is very clear, and deviation analysis okay, and comparison very good. But the cons is that didn't discuss the numbers of fingers since you have the definition, right? Just in the question mark, and there are no combination on the setup. So, and the conclusion is that the summary is that only experimental qualitative conclusion is given, but it has great notation, but there are no quantitative conclusion in experiment. Okay, so I would like to start the discussion section. And so in page 8, please. The projector. So I'm curious about why the surface energy needs to be minimized.
Because that you know that in the natural world that everything that they will tend to minimize the surface energy, just like when you look at the chemistry, they will tend to minimize their surface. They will tend to
The free
minimize
energy,
it.
right?
Yes.
And so where will those energy go?
Where do those energy the energy is they will go. I believe that they will go with the maybe they'll go with the Marconi flow really close.
Okay, so as you know, Marconi example of Marconi flow is that it will burst into a little balls, and just like the problem last year. So what's the difference between the fingers and the problem that do you know what?
I believe that because the viscous force will hold the mixture so that here it won't fragment to smaller droplets.
I'm
Here.
so sorry. Okay.
I believe because that the viscous force hold it,
Yeah.
so that here it won't fragment to smaller drop, because in the last year problem here the boundary of here is not the boundary at here is not very constructive. So I believe that
That's the main difference.
yes,
Yeah,
that's
okay.
the viscosity.
So is the viscous force still dominant in the Marconi burst, the little balls, or is the inertial force that takes the
I
dominant?
think the main reason that it won't eject it into smaller droplets is because of viscous stress.
Okay, that's okay. The next question is in page 11, just as we talk about the inertia. So as you know, when there is velocity, there may be some inertial force, right? Inertial
Yes.
So will the inertial force influence the?
Yes, it may, because that you know that the Marconi flow will decline. And so, but you can see that in my experiment graph. You can see that here, as I mentioned, it will have a maximum radius, right? But it will still have a little bit. It tends to grow a little bit because that it's still a very little Marangoni flow acting on this system.
Yeah, I know. And so I'm curious about. So you think the little error that is error or is just
Because we use a tracker to analyze what we measure in how we measure the maximum radius, so that we have to track many.
Okay. Oh, so in like in page 18 here, page 19 and page 29, and there you see that there's error bars in your graph, right?
Yes.
So I think the error of like this one is a little bit big. Could you explain it? So first, how many times did you do the experiment in each condition? 10 times. So you just measure the maximum radius by
using we use a ruler in the tracker to measure the maximum radius.
I got it. So do you use all of the 10
Yes.
groups you did?
Yes.
So this is maybe the minimum group. This is the maximum.
Yes.
Right. So what is the main reason causing that effect?
I believe that it may caused by the fraction. It may caused by the evaporation of the mixture.
Did you did it in the same temperature or
Yeah.
almost the same?
Almost the same.
Almost the same.
Yes.
Did you think the temperature will affect
Yes,
the?
it will.
Oh, yeah.
It will affect the evaporation rate and also the viscosity.
Yeah. Oh, very good. And I'm curious about. Did you think that the maximum radius is just proportional to the initial mass fraction of the mixture? Is a linear line or is not?
It's not. It's not because as I mentioned in this part, the maximum radius will look like this, and we put a constant k right here because this is as proportional. And I have a theoretical I have a derivation of the theory right in the backup page.
Great. Yeah.
Yes. I have calculated the viscous force and also the surface tension. And
Could you
also-
explain briefly?
Okay.
Just briefly.
First of all, I define the viscous stress at this, and I can calculate the surface tension, and then after calculating, I found out that the surface tension will be equivalent to viscous stress. And so that after I calculate with the surface tension gradient and also the viscous stress, and also I calculate the variation of the volume of the mixture, which that it evaporates, so I can get a characteristic radius.
So your theory is I think there's no flaw, but so did you think your experiment that the error bar is reasonable?
I think because that
Please
the
change to back to page 18. Yes. Thank you.
because I think, as I mentioned before, I think that it may caused by the evaporation rate difference or the viscosity difference, since that we cannot control the temperature perfectly.
But you say you almost did it in the
Yes.
same temperature. So almost in the same is about.
Maybe when we drop the some maybe some volume will be fixed on the syringe.
On the syringe.
Yes.
But
Here, this part.
okay. Oh.
I think this
Did you
is
think you know how to use a syringe?
Yes,
Right?
yes.
So did you think when you release it is you cannot always release in constant velocity?
I use this to hold it.
No, I said when you press the syringe, the fluid just get out. Right?
Yes.
So did you, if you can did you control the release speed since the I say about the inertia? And there's many complex
No,
parameters to this.
but I'll control the height up here. But and we think that we put the syringe close to the diagonal thing.
So how is the actually length of this?
1 centimeter.
1 centimeter. Did you try other heights?
Other height because they may cause a higher distribution, so we just try a 1 centimeter.
So you have a perfect theory, right? If you did it in a higher height of dropping the alcohol mixture, so what would you expect? Will the fingers be formed easily or not easily?
I think the fingers is formed because of the Marconi flow and the mystic stress. So I believe that it is no correlation with the height, how high they drop.
So you think there's no influence?
I think there's no influence, but it will influence the what can we see, but it will not influence the formation of finger.
Okay, so I think that maybe since that the height will influence the velocity, right? It will influence the inertia force, and the inertia force may cause some deviation since you only consider vicious force.
Yes, but
In your theory,
yes.
but if there's more inertia force at the higher heights, like
So you mean
so maybe some deviation will occur.
So you mean the inertia force is when you drop the velocity when you drop the drop.
No, the velocity is not same, but it may be some positive relationship between the inertia force and the dropping height.
But I believe that because that when you drop in the extreme height, it may cause the evaporate. It might cause the drop to evaporate when it's releasing.
But did you measure the evaporating
So
speed? Did you measure
I
in 10 seconds?
Yes.
Well,
we measure it. We
Right.
measure the evaporation rate.
Could you show us?
I measure it and the graph will I measure the evaporation rate and which is this in our theory, and we measure it. It will have a positive correlation with the concentration, and we measure it by putting a
So could you show us the data now? Or you didn't show me?
I didn't put it on this.
Okay, I have. So, next question. So, what's the relationship between the fingers formation and the length of diffusion? The length of the radius of diffusion.
So you mean what is the relationship between the finger's length and the radius diffusion?
Yeah.
I believe that because that the volume, because that with the same volume, the volume is limited, so that when the mixture will have a higher concentration, the radius in the inner part will be higher, so that the volume in the inner part will be more, so that in the boundary part of the mixture, the volume will be smaller, so that the finger will be smaller too.
Okay, so next question. So, did you measure the viscosity of the fluid?
Yes.
Where? Could you show us the of isopropanol?
I measure the viscosity of the dialactic, but I didn't measure this. But I believe that that
That's part of it.
isopropanol alcohol is much smaller than the dialactic.
If you were expected to do the viscosity of the outer layer and the inner layer, what graph would you
Okay.
plot?
Time's up. Sorry.
Also, in our further discussion, we're discussing about the evaporation of the alcohol mixture and the vicious force and the error bar created by experiment. In our discussion, we mentioned that the reporter mentions that temperature and will cause into evaporation, and evaporation may cause into big error bars. This is reasonable, but I think maybe next time you should do it in same humidity and same condition, in temperature condition, and when you consider heights are dropping, you should keep it constant.
questions of the reviewer.
So, honorable judges and worthy competitors, I am the reviewer from Team Uli Kanhua, and first I would appreciate the efforts that both reporter and opponent have put forth in this debate. So I have some questions for both of you guys. So, So first, what do you think is the fundamental driving force of the demolition? So
I believe that it's a mistrust in the Rangoni flow.
and
I agree with
okay, so and the second question is, if I dilute the acrylic paint with water, what do you think will affect the phenomenon of?
I believe that it will affect the viscosity of the diluted acrylic paint, so that this will be changed. This number will be changed in our here, so that the maximum radius will decrease.
I agree with the report.
Okay, thank you. So, and this is for the reporter, and as the opponent has mentioned, as you have mentioned that the isopropyl alcohol has the highest evaporation rate. So, can you elaborate more?
Evaporate. It will evaporate in our experiment
No,
because
I mean, can you elaborate more?
evaporate more.
Elaborate.
Evaporate.
Why it has the highest evaporation rate instead of like ethanol alcohol or butanol?
As I mentioned in the discussion part, I believe that if we use other kind of alcohol, it will have the same phenomenon.
So,
That
I mean, why do you think?
because I believe that this phenomenon is mainly caused by the concentration gradient, which will triggers because the mixture will evaporate because that it contains the alcohol. It contains the alcohol, so that it evaporates, so that it will cause the concentration difference, and the concentration difference will cause the
Okay,
surface
thank you.
temperature.
So, here's a question. So, as you can see, the reporter only examined the fractal fingers with naked eye. So obviously you cannot examine the fingers, like the structures of the fingers. So, what do you think, both of you? What do you think you can improve in your experiment to see the structure?
Maybe we can measure the distance between the fingers, or we can maybe use a different kind of acrylic paint.
Microscope.
Okay.
Typt up. Okay, the reviewer takes the floor.
So, honorable judges and worthy competitors, good evening. I am the reviewer from Team Kanhua, and now I'm gonna review the debate. Okay, so the problem statement, I will not use it again, but the focus from the reviewer is the formation of figures and the geometry and dynamics of the figures determined by different parameters. So, as what reporter mentioned, the phenomenon is the formation of fractal fingers split into branches, and about the theory, they have considered gravitational effects, concentration gradients, Marangoni flow, and surface energy difference, and characteristic radius. And as for the experiments, they have concluded an initial concentration of the mixture, initial volume, and the height of the acrylic paint, temporal evaluation comparison. And so, as for the pros and cons for the reporter, our team believes that the pros for the reporter is that he has clear visualizations of the experiment, such as the dynamics and geometry of the fingers, and they have experiments to test different parameters, and they also have graphs with interpretation and comparison between the theory and the experiments. And as for the cons, they didn't elaborate on certain equation used, and they failed to explain the measurement of the data. And they don't have certain, and some of the parameters are not tested, such as the type of alcohol. Yes. And as for the opponents, the pros for them is that they pointed out the loss of energy, and they also mentioned other factors that are easy to ignore, such as the control of strength and their efficient use of time. And as for the cons, they have ambiguous analysis the reporter's presentation, such as grades or something like okay. And they also mentioned problem from last year, not elaborating on the problem and its relation to the ones this year, which is the Marangoni bursting. And for the first discussion is, opponent asks the reporter what is the definition of finger, and reporter showed the picture of the experimental results. And as for the reviewers view, we didn't think that the reporter will define fingers because they didn't access it under the microscope. And as discussion 2 is, why do you use isopropyl? And the reporter said because the evaporation rate of alcohol is higher, and the reviewers thought that they should investigate different types of alcohol and elaborate more on the properties on the alcohol which cause different evaporation rate. And as in discussion 4 is the opponent asked why Marangoni flow forming tiny droplets instead of fingers, and the reporter said because of viscous force. And the reviewer disagreed with the reporter. We thought it's because the base of the experiment is different, with the Marangoni bursting is oil, and in fractal fingers it is acrylic paint. And for discussion 5 is the error-related large measuring using main reason causing deviation. And the reporter said that the evaporation of the mixture, and we agree with the reporter that evaporation of the mixture did influence the results, but we also consider that the main factor that influenced the experiment is the concentration.
Okay, time's up.
Thank you.
Concluding remark.
Hello, honorable juries and fellow competitors. This is the concluding remark from Timmy Silver. And first of all, we define the fingers as the perimeter of the mother jaw to the edge of the egg. And Marangoni flow is well explained in the theory part, that is derived from the concentration gradient that it will cause the surface tension gradient. And the surface tension will be equivalent to viscous stress. And also, the initial releasing method we control at 1 centimeter on top of dilute dark paint is because we want to avoid the environmental distribution, and it will also cause the fluctuation when the height decreases. And the opponent keeps telling about the initial force, which we found is not really important in our research. And since that only the forces that causes it to spread because of the Marangoni flow, which is caused by the surface tension gradient and also the viscous stress, because that the viscosity of the diluted arc is really high, which is like a 500 which is like a 500 CS. And we also believe that other alcohol fluids can produce the phenomena. And we can by testing their concentration or evaporation rate, and because that we can change the which is the JV constant in our JV number in our theory. And tiny droplets didn't occur in our report. And since that the viscosity of the arclay plane is really high, so that the viscous force will hold the mixture so that it won't eject into smaller droplets. And this is the end of my talk. Thank you.
Okay. Questions from the jury?
Could reporter show the formula on page 13? Sorry. Did you check anywhere on your report? Did you check this formula against your data?
Do you mean what I changed?
To check this formula whether it's correct or not, whether it agrees with your experimental data or not.
Yes, it agrees.
Yeah. Which page?
In my experimental results,
Yeah.
it kind of agree with mine. Because we think that it is the same reason that why it will have a maximum radius and also why it expand and the maximum radius. We believe that the reason is the same. So we obtained this theory and we found that it fits our theory.
But I did not see the formula here.
The formula.
Anything reminiscent of the formula? I only see the experimental data.
I changed the initial concentration and the initial volume and the height of the object, which is these three parameters in this formula, and this line we obtained is by calculating by that theory.
Thank you.
Any other questions from jury?
So from question by the reporter, in your conclusion, there's a point you mentioned is tiny droplets. The second point, can you explain it more? That statement?
I know that because it won't fragment into tiny drop. Because that the viscosity of the arctic plane is larger than is much larger than the oil, and also so it will hold it so that it will not fragment into smaller droplets. Because that the reviewer and the opponent they both mentioned about the droplets.
More questions?
We didn't see the droplet when we are doing the experiment.
No questions? Okay, no questions. Jury, please consider the case. So for reviewer, sorry, reporter. For reporter, 8, 5, 7, 6, 5. And for opponent, 7, 7, 6, 6, 6. And for reviewer, 7, 7, 6, 7, 7. Okay? So maybe 10 minutes break. Okay? So we will be back in 10 minutes. Challenge is the reporter for the project.
Honorable judges, for the opponents, this is the team Uli Kanhua, and we would like to challenge problem number 8, Euler's pendulum.
Okay, sorry, we reject that problem.
So, next we would like to challenge problem number problem number 6, mechanical magnetic oscillator. Number 6.
6. No.
Sorry.
Available problem.
So it's not available. Then we would like to challenge problem 15, pancake rotation.
So team Wu Kanhua will accept the challenge.
Okay. So please write your name.
Reporter, please take the floor. Hello everyone, I'm the reporter from Psychoris. Okay, I'm going to report the number 15, 10K rotation. Okay, this is outline. We will introduce and then the theory, set up and experiment, and then conclusion. Okay. The problem statement is place a few balls in a round container. If you move the container around the vertical axis, the balls can move directionally with the movement of the container, or they can move in the opposite direction. This is a key question. Number one, will the amount of the balls affect the motion of the balls? Number two, which parameter will affect this phenomenon? Angular velocity and size of balls, or the bottom area of the container. Okay, this is our experiment video, and in this video we can see the black ball is moved directionally with the container, and in this video we can see the black ball is moved opposite directionally with the container. Okay, let's start off the theory. This is the notation we will use. Centripetal force. When we rotate the container with a vertical axis, there will have a centripetal force toward the center of the circle we rotate, and the container will have the centripetal force, but because of the inertia, the balls will gather in the opposite direction of the centripetal force direction. And the friction force, when the balls is gathering at the walls of container, it will have a friction force against the rotation of it. Okay, it's coverage rate, because we think the rotation motion is related to the ball size and the container size. So we'll have a coverage rate is the cross-sectional area of balls over the bottom area of the container. And this is the prediction. We think the coverage rate of balls is high, the opposite directional motion will happen. And the coverage rate is low, the co-directional motion will happen. Okay, let's simply cut the circular motion into 4 parts. Okay, let's start off the co-directional motion. First, when the container is rotating, you will have a centripetal force. And because of the inertia, the balls will gather in the opposite directionally with the centripetal force. And in a similar fashion, when the centripetal force is upward, the balls will gather downward. So, because our container is rotating by a vertical axis, so the centripetal force will also rotate too. So the balls is moved co-directionary. Okay, let's start the opposite directional motion. First, the leftward centripetal force axis. The force will carry rightward. So here will be a dense area, and because here's density of force is higher than here, so the friction of the dense area will higher too, and the loose area, because this density is lower, so you don't have much friction against the rotation. Second, when the centripetal force is upward, the dense area before will have a strong friction against the rotation. So here, the force here will move a lot, and in a second, when the centripetal force is upward, the dense area will be here, and the loose area will be here too. Okay, in the third, the centripetal force is rightward, and when this situation, the force is the black ball is in a loose area, so it can move freely. When the downward centripetal axis, because the black ball is in the loose area in the third step, so it can move freely. So when the centripetal force is downward, the black ball will go up. So the opposite directionary motion will happen. Okay, this is our experiment setup. We use Lego blocks to make a rod and EV3 to provide us a constant angular velocity, and round container and plastic ball. Okay, this is the tool we use. We use tracker to measure the angular velocity, and EV3 to generate the constant angular velocity, and Excel to create the graphs. Okay, it's the experiment process. We put a few balls in a container, and we change the balls amount and the velocity of the container to do our experiments. Okay, this is the size of experiment device. Our round container's radius is equal to 4.5 centimeter, and small ball is 0.5 centimeter, medium is 0.7, and large is 0.9. This is our experiment results. We have two angular velocity. The lower is 200 and higher is 400 degrees second. We use the coverage rate we talked before. So the small balls is equal to 0.012 times n. N stands for the number of balls, and the medium ball is this, large ball is this. Okay. In this chart, we can see the plus and the minus. The plus stands for the co-directional motion, and the minus stands for the opposite directional motion. In this chart, we can see this is a small force result, and when we have a high angular velocity, when the force amount is 37, it will start the opposite directional motion, and the lower is 2. This is medium force. When the medium force amount is 21, it will happen the opposite directional motion, and the lower is 2. Okay, this is a large ball. The large ball, when the large force amount is 13, it will move opposite direction, and the lower is also 2. Okay, this is our result of our in high omega. When the force coverage rate is higher than this, the opposite directional will happen, and vice versa. And this is also true. When higher than the opposite directional motion will happen. Okay, so the coverage rate isn't less than the minimum force count, that will let force move in the opposite direction. So we put a few force in the container and record its motion. And I think the motion is related to the centrifugal force and friction force. And this is our result. We think the coverage rate is important in the result. And the angular velocity is not really affect the motion.
Okay, time's up. So, questions from the opponent.
Okay, so I'm the opponent from Team Uli Kanhua, and I got some brief questions for you. And please turn to page 6. Yes, and please look at the GIF here. Do you see that the container is not really rotating? It's also like shaking, because your structure of your Lego brick is not really that.
Yes, I think our structure is not really. But
Okay. So please turn to page 13. 13. Okay, so you say that the cover rate of the marble is a important parameter, right?
yes.
And have you considered that if you put a lot of marble in this container, there will be a margin between those marble? Do you consider this?
Yes.
And will that affect the experiment result in your opinion?
Do you mean if I put a lot of force in?
Okay, so consider that there's a marble right here, and there will be a margin between the marble.
Yes.
So, in your opinion, will that impact the experiment result?
I think it not affect our experiment result.
Okay, so please turn to page 19. You state that there will be a centripetal force when the container was rotating, right?
Yes.
And is that the main reason why the marble in the container was going counter-rotating or rotation?
Sorry, so time's up.
Okay.
Honorable judges and worthy competitors, I'm Ryo-chan from Team Uli Kanhua, and today I'm going to propose problem number 15, interpretation. Here's the problem statement, and I will not repeat it again. And the reporter's focus was on the amount of the balls affecting the motion and the parameters affecting this phenomenon. As the phenomenon, the reporter has mentioned that in opposite directional movement, and that will be a discussion I will discuss later. And as the theory, the reporter only has the force analysis. They don't have the quantitative theory, so I'll discuss this later. And as the experiment, here are some parameters that the reporter had investigated. The first one is ball size and the container size and the coverage rate of the marble. And here are some pros and cons for the reporter. As pros, the reporter has qualitative explanations and images with labels showing the phenomenon. And as cons, he is lacking in a bit of clear videos to demonstrate the phenomenon and efficient data. And here are some discussion I would like to discuss with the reporter, and now I would like to invite the reporter to get on stage. Okay, so as we discussed previously, could you turn to page 13? You've said that the margin between the marbles doesn't cause a lot impact in this experiment result, right?
Yes.
But
Okay, because if we place a lot of balls in a container, it will have a maximum coverage rate.
Okay, so from my perspective, I've seen your video that you show in your PowerPoint, and there's not really that much marble in the container that we can ignore the margin between the marble. And from according to my observation to this phenomenon, the margin between the marbles does cause a lot in the experiment result, and that's a really important parameters to impact the experiment result. And could you turn to page 33?
Okay.
You say that when the area proportion of the marble was rising, the movement of the marble will go from counter-rotation to rotation, from rotation to counter-rotation, right?
Yes.
And from my perspective, I've seen that there will be a boundary condition between these two movements, that the marble will go stalling. It's not really like stop in the same position, but like rotating at the same area, same small area, and I think that would be a boundary condition for this phenomenon.
Do you mean the transition zone between the directional motion and
Yes.
opposite? I think so, but as you can see, our coverage rate is uncontinuous. So maybe the transition zone is between here and here.
Okay, so here's my suggestion for you, that you probably can place some smaller balls that will fit in this margin that you've set in your experiment.
Okay.
And please turn to page 27. In this video, we've seen that there's a black ball in the container and also in the cluster of the marble. And could you explain that will the arrangement of the marble in the cluster move when the marble or the cluster was going counter-rotating or rotating?
I think a range of the marble would not affect the motion. It will do whether it's directionally or opposite directionally.
Okay, so please turn to page 30 again. 31, maybe. 33. And we've seen that there are two movements in this experiment result. That is counter-rotation and rotation. And do you think that the area proportion or the RPM of the container will affect the angular velocity of these two movements?
The angular velocity of the container will affect this motion's angular velocity.
Yes.
But it doesn't affect if it is directionary or opposite directionary. It will only affect the angular velocity of its motion.
And from my perspective, and also according to my observation and my experiment, I saw that when the RPM, also the rotating speed and the angular velocity of the container was rising, the boundary condition is also stands for the stalling motion will rise. As we can see that there are counter-rotation in this movement, and from my perspective and according to my experiment, I've seen that whether the RPM of the container rise or not, the angular velocity of the cluster and also the marble on the outer side of the cluster won't change a lot. But the RPM of the container do really impact the angular velocity when it is rotating. Not counter-rotating, rotating. The same position, the same way as the container moves.
Yes, but I think that if the angular velocity of the container is increased, the period of the centripetal force is change fast. So its motion's angular velocity will increase too.
Okay, so could you define what your angular velocity of the movement means?
Yes. In this video, we can see the blackboard is do the opposite directionary motion, and if the container's angular velocity is increased, the blackboard will rotate more fast.
Okay, so because you have already turned to this page, so I'm going to discuss this with you. And as we discussed previously, we've seen that there are shaking of your camera, right?
Yes.
So do you think that if your camera was shaking and you use the tracker to track the marble in this container, will it affect your experiment result? Will that be a deviation?
Yes. We use tracker to the video we use tracker is another video. It didn't have the marbles on it. It only the machine is rotating. We use the video is not this video. We mount the camera on a place.
Yes.
So the video won't shaking when we use the tracker.
So okay, so you put out a video that the camera is shaking, and your experiment result is from another video that the camera wasn't shaking, right?
Yes.
Okay. And could you turn to page 3 or page 4 there, which you put out page 5. Sorry. You say that which parameters will affect this phenomenon, and you put out the angular velocity of the container, right?
Yes.
So did you investigate these parameters in your experiment later? Because I didn't see that you've changed the angular velocity of the container.
Yes. We have two angular velocities of the container. One is 200 degrees and one is 400 degrees.
So do you think that two angular velocity is able to show the trend of the experiment result?
Because in our experiment result, the angular velocity won't affect the motion. So
But you've just put out 2 angular velocity of the container. But how can you say that it won't affect the experiment result by just putting out 2 angular velocity of the container?
because in our theory, the motion is related to is relating to the friction and centripetal force. If I increase my angular velocity, the centripetal force will increase, but whether it will opposite directionally or co-directionally, it's more related to the friction.
Okay. So before you conduct the experiment, you've claimed that the theory was right? So I think that's not really that proper, because when you're conducting the experiment, you have to prove that your theory was right.
Yes.
But not really that you claim the theory was right and then just put out 2 different variation in the parameters and then says that your theory was right. Right? Because you just put out 2 angular velocity and you say that this did prove your theory was right. But I think that's a little bit improper.
But I think it's not, because 2 angular velocity one is very low and one is very high. So I think it can stand for if I increase the angular velocity, it's from very low to very high. It will affect the motion.
Okay, thank you. What if, okay, another point is that, do you think that this experiment result or this phenomenon do have a boundary condition?
I think yes.
Yes?
Because if our coverage rate is between the co-directional motion
Yes?
and opposite direction motion, it will have a transition zone, because the friction of this motion is not strong enough against the rotation. So this condition the balls will rotate in a place. It will rotate it.
So you're
It
saying
will do a circular motion.
you're saying that the boundary condition is not a range, it's a line. Right.
If I use it will be a range, but
Yes?
the range isn't very wide.
Okay, so how do you think the boundary condition will change if you change the parameters you put in your experiment?
If the coverage rate between these, the transition zone will happen.
Okay, so according to my observation to this phenomenon, I've seen that when we increase the RPM, also stands for the rotating speed of the container,
Yes.
the boundary condition will elevate, which stands for the area proportion to meet the condition to let the boat go stolen.
Yeah, sorry, time's up.
Yes.
So opponent, please summarize.
Okay, so after this discussion with my reporter, I've seen that there are a few flaws in this experiment, and they didn't put out that much parameters as I mentioned, and some of the factors that will in fact impact the phenomenon, which for example, the shaking camera or the RPM of the container, they won't really consider it when they are conducting the experiment. So I think that's some points that the reporter can improve. And I do really appreciate the effort of the reporter when they're conducting the experiment and reporting. Thank you.
100-pager setup. And you mentioned that you changed the angular velocity of the plate, right?
Yes.
And you track the motion of the balls by using tracker, right?
We don't track the angular velocity of the balls. We track the angular velocity.
But anyway, you track the data by using tracker, right?
Yes.
And how do you make sure that it is not the movement of the plate instead of you want to track the motion of the balls, but how do you make sure that you won't track the movement of the plate? Okay.
Do you mean I track the container?
No, I mean if you set the camera on top of the setup,
Yes.
like here, and how do you make sure that, and you're tracking the position of the balls, you can ignore the movement of the plate since.
Yes. So we don't track the balls. We don't track the balls angular velocity. We only track the container's angular velocity.
Okay, I would like to skip to the next question and turn to page like the qualitative explanation about the centripetal force. And how, like this, how do you define the density of the area?
In density area, it will in the opposite directionary of the centripetal force, and in a dense area, the force will gather. But in a loose area, the force can move freely.
Okay, I know your opinion. So the question for both reporter and opponent, do you believe that centripetal force is the main cause of the phenomenon? Reporter first.
The centripetal force is the main reason in a directionary motion, but
Okay,
in a
thank you. And for the opponent,
No, I don't agree with the reporter.
and what do you think is the main reason?
I think the main reason is the inertia and the position of the marble in this container and in this cluster also. And this.
And for both reporter and opponent, do you agree that friction acts in the system? Friction.
Yes.
yes.
Which is kinetic friction, rolling friction, or static friction?
I think it also have the kinetic friction and rolling friction.
For the opponents.
Yes, it did. It do really impact the phenomenon, but I don't think that there are both friction in this phenomenon.
For the opponent, do you think?
Sorry. Can you stop?
Oh, thank you. You can start early if you want our teammate. Okay, we would like to start. Honorable juries and fellow competitors, I'm the reviewer from Team Excel here. Today I'm going to review problem number 15, pancake rotation. problem statement. Place a few balls in the round container. If you move the container around the vertical axis, the ball can move co-directionally with the movement of the container, or they can move in the opposite direction. Explain this phenomenon and investigate how the direction of movements depends on relevant parameters. And we'll mainly focus on why the balls move in opposite direction instead of the co-directionally, co-direction, and a critical casting density that leads the ball to move in the opposite direction, and how different parameters, for example, the friction, rotation frequency of the container affect the phenomenon. For the review of the reporter, in the phenomenon, she mentioned about the counter rotation phenomenon and also the observation. Theory is about the centripetal force, which he believes that will cause the phenomenon. For experiment part, they change the parameters, include the coverage of the balls and angular velocity. These are the pros and cons for the reporter. We believe that they have a clear observation video which can show their well-built setup. They lack of quantitative explanation, which can rule the theory line in his experimental results. The setup is set with high reproducibility, but we suggest that a camera can be set on top of the setup to track the motion of the balls. And they failed to simulate the phenomenon. The reporter also separated the phenomenon into states for us to clearly understand what is the phenomenon about. However, the reporter lack of experimental analysis and parameters. For review of the opponents, we believe that they indicate reporter lack of parameters affecting the phenomenon. Also, they discuss a qualitative explanation about the reporter mentioned about the centripetal force. However, they missed the discussion on the experimental results and also how the reporter get the experimental results. Yes, and they lack of explanation of comparison between the theory and their results. They cannot connect together. And for the discussion about the setup, the opponent believes that the shaking camera will cause some deviation, and the reporters they use tracker to track the position in another videos, but the reviewers support that the camera position will change. That is. And for our question, we believe that centripetal force is the main cause of the phenomenon. We believe that it doesn't affect that much. The main reason is the static friction that causes the ball itself to rotate. Or what is the main force causing this phenomenon? We believe that the static friction that prevent the ball from rolling with the plate together, so that the ball remains in a stuck state. For the pointers, we believe that a simulation can enhance the reproducibility and we can compare the simulation results with our experimental results. And the qualitative explanation, we believe that some balls are pinned and some balls move in the plate. So kinetic friction and static friction should also be discussed. For parameters part, we believe that changing friction can affect the experimental results. And the deviations, but we believe that they should consider energy loss in their reports. Thank you.
Concluding remarks on the reporter.
Okay, thanks to our opponent and the reviewer. Okay, we have to conclusion remark. Okay, the Lego brick is easy to set up, but if we want to check the angular velocity of the black ball, we can set the original points at the center of the container. And in this condition, we can accurately get the angular velocity of the black ball. Okay, when the ball's motion is called directionary, the centripetal force and inertia is dominant, and when it's opposite directionally, the kinetic and rolling friction is dominant. Okay, talking about the transition law, because our coverage rate is discontinuous, because we can only put one ball. So I think there is a transition law, but our coverage rate is not continuous. So we can get a transition law's coverage. Okay, thanks.
Okay. So, questions are from the jury.
Question for the reporter. Since you mentioned that friction a superior role in the phenomenon, do you think that do you ever try to change the smoothness or the roughness of the bottom of the container? My question is, suppose that I noticed that you did not do, but do you suppose that if you try with a smoother or a rougher bottom of the container, will it significantly?
No, we didn't change the container.
But if you do it, do you think that it will significantly affect your result?
I think it will affect the result because it's more hard to protect. So I think if the container's bottom have more coefficient, the direction motion will happen in less than our results.
Thank you.
More questions? From jury?
So, for the opponent, you mentioned the margin between the balls
Yes.
affect the result.
Yes.
What's different between the opponent mentioned the coverage rate? What is the?
Because if we view the cluster, which stands for the balls, all of the balls in the container as a system, the error proportion wouldn't be just the marble itself and also the margin. And in my experiment, I proved that it's right. So I asked the reporter this question.
I agree with the opponent's ideas. It's the coverage area. In my opinion, if the coverage area is bigger, it means that there are less. The balls are not. The balls are restricted to move. So it means that they have higher possibility to be pinned on the plate, so that it happens. The rolling of the ball will be more frequent instead of like turning with the plate together. But if the plate is covered with all of balls, the balls cannot move. Yes.
But in my experiments and theory, I don't think the margin of the container we put the balls in it will affect motion, because the margin won't affect the friction and the centripetal force that cause the opposite directional motion. So I don't think the margin will affect the motion.
The reviewer believes that if there are more balls, even if they are, you mentioned that the centripetal force, the balls in the higher density area cannot move, so that it is high. It has a higher possibility to be in a stuck state.
More questions from jury? Okay, so time for preparing waiting. So for reporter, sorry. Seven, 4, 4, 6, 6. And for Poland, 7, 7, 6, 7, 7. For reviewer, 8, 8, 7, 6, 7. Okay, so 讲好。
我昨天有评到，刚好也评到对象另外一个对，所以投影片几乎是一样，所以这你要注意一下。
另外一个队是什么？哦，同校2个队是共用同一个投影片。建议还是就是虽然是不同队，但是自己做自己的投影片会比较好。昨天有一场的话，因为这个关系的话，那一队被一个 reviewer 扣，本来譬如说5分，他把它扣到3分。对，所以昨天也有发生这样的状况，在我的场。
我本来想刚提啊，就算了，我就可能再会。
We would like to challenge problem number 2, oscillating sphere.
This is Team Uli Kanhua and we accept the challenge.
Okay. So problem number 2, and please write your name on the Okay.
This is Xu Kai-yi speaking from Team 物理看花 representing Taipei Legal High School. And now I'm presenting problem 2, oscillating sphere. So first, here's my presentation outline. So first, I will go through the problem statement, and then the phenomenon, theory, experiment, and summary and conclusion, and lastly, the reference. So for the problem statement, it says a light sphere with a conducting surface is suspended from a thin wire, where you can see it on the GIF. And when the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, the sphere will start to oscillate. And our focus is to first explain the phenomenon, and second, investigate the relevant parameters. So here, the phenomenon is pretty clear that the oscillation decreases as time goes. So here's my theory. First, the most fundamental one is damping. To talk about the damping theory, we must start from the most basic form, where there's no magnetic field generating. So there are different elements of damping without magnetic field. So first we got the air resistance, where it is proportional to velocity and it would fit to an exponential decay. And the next is the friction as suspension, which would fit a column damping and it would fit to a linear decay. But with a magnetic field, the oscillate would have a larger damping, since we know the damping is like you can add it up. So next, we'll enter the theory part. So we assume that the sphere has a radius given by an thickness h, where the radius is a, and h is much smaller than a. The material density of the sphere is given for low m, and we will get the mass of the sphere as m, the equation here. And we can also calculate the moment of inertia of the sphere. So next we'll talk about the electromagnetic brake. So from Ohm's law, we would know that the current density would equals like this, the equation, and due to the conservation of charge expression, we will get that the divergence of current density equals the partial of charge density with respect to time. And now, in our experiment, we'll consider the distribution of the electric charge is constant. So we'll get that the divergence of current density is 0. Therefore, we got the equation down here. The next one, with differential form of Gauss law, we will have the charge density divided by the permittivity would equals the divergence of the electric field density. And combined with the equation that we get from the last page, we will get that the charge density would equals to negative permittivity times the divergence of the velocity across the magnetic flux density. So by Poisson's equation, we can find the electric field, which if you observe it, you can find that it's actually the same as the differential form of Gauss law, like this equation here. Okay, so now we're talking about the force and the torque. So first, as we know, the sphere, we're talking about the whole system, so we need to use integral to calculate the force and the torque. So with some calculation, we'll got that the net force on the sphere is 0, which is quite reasonable since we only turn it, and while the sphere is not moving around, it's only rotating. So we'll get the torque as the equation down here, and we then have putting in the moment of inertia times the angular acceleration. Next, combine these two equations, we'll get the formula down here, and which indicates, since it's a ODE differential equation, and it will indicate that the spin decelerates exponentially, which omega will be proportional to exponential to the power of negative alpha over t. So now in our experiment, our material density is shown, and the electroconductivity of the sphere due to its material, we choose iron, and this is our number. And here's our equipment setup. So first, we use standing clip to hold the whole wire to ensure it's stable, and the thin wire, hollow metal sphere, and also the magnetometer to detect the magnetic flux in the whole experiment. And for how to generate a stable magnetic field, so we first use current power supply to Helmholtz coil, which generates a stable electric field. And we use repurposed electrometer to ensure that the whole experiment goes well. So first, as I mentioned before, the most basic form of the sphere damping is without no current in the coil. So we can get that the only thing we're focusing on is the A/1 number, which should be the ratio of the damping. And as I mentioned before, the damping should be it could be add up. So we can define this like A/1 number without any current triggering the whole coil as the damping effect caused by the torsion and the air friction, the air resistance, sorry. So next, we'll start from 0.9A and we'll get different numbers of A/1, which is the damping ratio, and just some different numbers. And the results are that, just like the aforementioned, the magnetic flux density would be powered proportional to the A/1, which is here. The alpha would equal to, those are all constants, so the only variable in this equation is the magnetic flux density powered. So that would be our whole experiment and the setups. But for the improvement, first, straight and thinner wire to suspend the sphere would be required since, as you can see in our setup, it is actually quite a difficulty for us to ensure the whole thin wire is straight. So it may cause a little bit deviation when rotating the ball, and also the torsion caused, the damping caused by the torsion. And then, more ideal conducting sphere since, and also more materials the sphere is, since I just mentioned that in the equation, the permittivity and the charge density are all impacted by the material of the sphere. So we could test more different materials in our experiment to examine our theories and more accurate photographing angle of view. So this will be end of my presentation. And here's the reference. Sorry about that.
Okay, so questions on the opponent.
Okay, so what are your forces that cause damping when there is no magnetic field?
So first we got the air resistance, and next we got
As a
the
friction
torsion.
as suspension, and also
Yes.
air gap.
The
Okay.
air resistance, yes.
Thank you. The damping effect will be more significant if you use a hollow sphere or a solid sphere.
Due to the fact that we didn't check if it is if we use a solid sphere, but
Okay, thank you. And what is the conductivity of the sphere that you're using?
the conductivity,
Yes.
yes, mentioned it, here, the electroconductivity of sphere, since the material is
And how
out.
can you compare your theory with your experiment? Or do you have any relations, or can you explain about your experiment?
For our theory, we aim at proving the equation down here where the angular acceleration is proportional to the magnetic flux density squared.
So, back to page 11, thank you. So how did you consider friction as suspension, and also, how did you consider friction inside your theory?
Yes, just like what I just mentioned, since the damping could be add up, so I can see if I get the damping effect caused by the air resistance and the torsion before I test
So do you think that Lorentz force is the main cause of this phenomenon to happen?
Sure, because the larger damping is definitely caused by an electric field which I triggered.
Okay, thank you. And what do you think that using different sphere will cause the moment of inertia difference, and will it cause the oscillation frequency to be different?
So first of all, if I change the material, first it would impact the moment of inertia, and next is the
Okay,
conductivity.
thank you.
Okay, time stop. So, opponent, do you want to start early? Or you can start early if you are ready.
Okay.
Yeah, take your time.
Dearest fellow competitors, this is the opponent from Team Excelsior, opposing problem number 2, oscillating sphere. Problem statement. A light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, thereby twisting a wire and then released, it starts to oscillate, investigating how the presence of a magnetic field affects the motion. And due to your problem statement, I believe we should mainly focus on how does the oscillation of the sphere act, and how will the magnetic field affect the motion, and how do relevant parameters that will affect the oscillation of the sphere. For the reporter's outline, first of all, his theory includes a damping effect and Ohm's law, Gauss law, and Poisson's equation. However, he did not conduct any experiment, and therefore he cannot give any experiment or error analysis between his theory line, and he don't have the deviation explanation. These are strong and weak points for the reporter. First of all, he had a clear observation, video, and setup, and he explained the phenomenon. However, he did not focus on the math calculation part, and he focused on the math calculation part instead of the physics inside, how Lorentz force is acting inside the system, which the opponent believes that Lorentz force is also the main reason that causes this significant damping effect. And he can release the sphere stably, since he mentioned in his report that he cannot control the setup of the releasing. And he missed the experiment of non-uniform magnetic field, since the problem statement has asked for to investigate how different kinds of magnetic fields affect the motion of the sphere. Sorry. And he did not discuss about the qualitative explanation, how damping force is generated. And in his theory, he cannot add the friction into the fitting curve. And he did not consider a lot of parameters, and he did not conduct experiment and analysis to prove lots of equations shown. These are points that I want to discuss for the further part. So for the oscillation analysis, I want to discuss about the rotational inertia, how it will be changed with solid sphere and hollow sphere, about the structure of this conductive sphere, metal sphere. And I also want to discuss how you measure the torsion constant inside the system, and how damping effect will cause the decay time to be different. And inside the force, of the experiment, I believe that friction and resistance will be the energy consumptions or dissipations. And I also want to discuss how magnetic field, since the problem statement has asked for to discuss about how different magnetic fields affect. I believe that magnetic field can be separated into uniform or non-uniform magnetic field. Well, in his experiment, he's using a Helmholtz coil to provide a uniform magnetic field. But I also want to discuss if a neodymium magnet is beside the sphere, it causes a non-uniform magnetic field, and how would it affect the experiment result. And also I want to discuss the measurement of some of the forces, such as the eddy current on the sphere, and also Lorentz force, its direction and magnitude, since it has relation with the eddy current. And for the experiment parameters part, although he did not conduct too much experiment, I want to discuss about the magnetic field, its magnitude of the magnetic field, and how induced angle with the rotational axis would change its from perpendicular to parallel. I want to discuss how the angle changes the force of the magnetic field. And for the conductivity part, I want to discuss what kinds of conductivity or material is he using and how he's coating the material onto the sphere. Thank you.
Okay, so discussion.
So how do you define the phenomenon happens?
Define the phenomenon happens. So for our observation, we can. I'm sorry if I didn't clarify that how my experience have done, but overall, what I've done is just inputting different.
So how do you define? I mean, like, how do you say that there is a damping effect causing inside the system?
Oh, well, I'll say that I need to compare it with when no current is inputting for the whole
So
coil.
in this part, I would suggest the reporter for using decay time of different kinds of current inside the system, giving different kinds of magnetic field. And I believe that by comparing the decay time, we can have a more standardized definition of how the phenomenon happens.
Oh.
Do you agree with that?
I would agree that is a way to explain the damping which caused by the magnetic field.
Please turn to page 11. So what is alpha inside?
Alpha?
Yeah.
The alpha would be the angular acceleration.
As far as I know, the alpha in this reference means the decay time that I mentioned above. However, you doesn't seem to know about the decay time. Can you explain about the decay time? Like, do you even know about that?
Decay time, like what our experiment is focusing on is to talk about the relationship between A/1 and the, like, if I didn't clarify this graph enough. So as I mentioned, we used we use the situation when there's no current as the base for our whole experiment, where you can see that the graph starts from 0, which means there is no electric inputting in the whole system.
So I'll explain decay time for you. So decay time is actually a standardized definition when it reaches to 37% of its original amplitude. So I believe that through comparing the decay time, you're able to have a more precise comparison between each data. And also, you're using the decay time inside your theory, and however you cannot explain it next I want to ask about a qualitative explanation. Why do you think that Lorentz force acts inside the system?
Well, so we have to go back to our page where
Can you describe how it is, like the qualitative explanation, how Lorentz force is caused?
qualitative explanation. Okay, I'll say that since we got a magnetic field here, or can I write it on the blackboard?
Yeah, sure.
So first of all, since we all agree that the problem should be discussing about the radical actors.
Yes.
So I will just focus on this field right now, where the sphere is here. So when I rotate the ball, there will be a velocity, correct? And the magnetic field here. So which these two will cause a force to make the motion of the sphere decrease more quickly, which is damping.
So you
correct?
mean the B cross B inside your theory is the Lorentz force?
Well, I'll say that equation.
I believe that B cross B inside your theory, inside this part, I believe that it means the electric field of the theory inside the theory.
Yes.
So it does not match with the Lorentz force that I'm trying to ask. So here's actually an explanation about how Lorentz forces act inside the system. Please read the next page. So since we all know that the spherical object can be assumed as it is infinite coils, so we can assume that this is infinite coils integration. So in this case, I'll assume that this is a coil rotating in a counterclockwise direction. So in this case, we know that there is a Helmholtz coil providing a magnetic field given by the Helmholtz coil. So it's going in this direction from left to the right. And after it starts to rotate in the counterclockwise direction, it causes the magnetic field going this far. The contact area actually increases. And from Lenz's law, we can note that it generates a force opposite to the direction of the sphere rotates, which we can note that the eddy current on the system acts in this direction. And therefore, from the Lorentz law, right-hand law, since we know that there's always a magnetic field B going in this direction, and therefore this point is where the magnetic field is acting, and I should be the Lorentz eddy current I mentioned above. And through Lorentz right-hand law, we can know that this Lorentz force always acts in the opposite situation where the spherical object is trying to rotate. And I believe this is why it causes this significant damping effect caused by this magnetic field and also the eddy current on the system. And do you agree with this explanation?
Well, I agree, since I just mentioned I would simplify the whole motion as an invisible force, since you can observe like that force which lowered the whole motion more quickly.
Okay, so please turn to page 22.
22. So, where is it?
Sorry, page 5, I think.
5? Okay. Oh, sorry. Okay.
So, in this equation, what is this part?
Well, that is just a general solution for the damping effect.
So, is this damping effect only considering the magnetic damping, the damping coefficient, or is it considering the air resistance and friction as suspension?
No, that is just a general solution for like whatever kind of damping. So that contains.
Can you turn to like the place where this is actually t divided by alpha?
Oh, okay, sure. So like this is just like the whole motion is damping, right?
Yes.
So I use the general solution for damping and to fit the curve, which is the data points I get.
So in this part, I believe that you did not consider the friction as suspension and also the air resistance. So the original theory is written in this part. Am I correct? So, and also like this part.
Yeah.
So I believe that in this part, I'll give a suggestion that you can actually add a fitting constant of the coefficient of the damping coefficient for the friction and the air resistance by measuring the periodic time and also the oscillation motion of the sphere rotating without the magnetic field, and therefore we can measure another coefficient of negative omega t. And after that, we can like times it together, and we can get this equation that it equals to this, like, so that you can consider the air resistance and also the friction as suspension inside your theory. So this is my suggestion for the modification of your theory.
Okay, I'll set that.
Next, I would like to discuss about the experiment part. So, how many experiments did you even conducted?
So first, I'll count this one in too. So one.
Please turn to the chart. Like.
Chart. Oh, okay, sure. You mean the graph, right?
Yeah.
Oh, here.
So where is the deviation? Like, are there any error analysis or are there any error bars in this part? Or you only conducted once?
Well, I've conducted it several times, but I'll say it's my mistake for not putting on the error analysis.
Okay, so what do you think by changing the magnitude of the magnetic field will affect? So it will cause the Lorentz force to be bigger and cause a greater
Well,
segment.
I guess what you mean is the value B, right? Since I mentioned it, like here. So of course,
Yes.
it would be square root 2 with relationship of the damping effect. I'll say.
Yes.
Okay, thank you.
Okay, opponent summarize.
So in the previous part, we discussed about the definition should be included to describe whether the phenomenon happens to or not. And in this part, I suggest you record for using the k-time to compare with each experiment data how the k-time affects, And through this, we can know the comparison of how damping effect is significant. And Lorentz force is related to magnetic flux density. However, the reporter keeps saying that B cross B in his theory, which means that the electric field is actually the same as Lorentz force. And when suppose that the ball countless of coils, the added current generated can prevent the ball from rotating. And the reporter also agreed with my qualitative explanation how Lorentz force is caused. And the error resistance and torsion constant should be considered in the damping part. And I also give a theory modification suggestion for his report. And he did not have any error bars inside his graph, and which the
Okay, hands up.
thank you.
So the viewer takes the floor.
Okay, so thank you, the opponent and the reporter. So the first question I would like to ask is, what is the main parameter of this problem? So opponent first.
So the magnetic field, like the magnitude of the
Sure.
magnetic field, the magnitude of magnetic field,
Any other? No.
and torsion.
Okay,
So first the B, like what the opponent just mentioned, and of course the material of the sphere.
Okay, so the next question is that the reporter, how would you measure the current?
The current? Oh, we use a direct current, so like I change the current that I input. So that is not what I measured. Like I put it.
Okay.
Yes.
Okay. So if the current will flow on the sphere, does it flow on the surface or flows all over the sphere?
I believe that it's over the surface of the sphere when it's rotating.
Well, I agree with that since it's a field which works on the whole sphere. Right?
Okay. So next one. So what will happen if you change the wire's conductivity?
The wire's conductivity, well, I'll say, I'll consider mainly the wire impact the whole motion is the kappa, which I mentioned, the torsion of it. So I don't think the conductivity would play a significant role in it, but kappa might be.
Okay. So
I don't think the conductivity will change the experiment result, but however, by changing the material of the wire, it actually causes the torsion constant to be different, and therefore the damping coefficient here will be different.
So what damping? Also, you mentioned damping. So what damping solution is happening in this problem?
What damping solution?
Which damping type?
Which damping type?
It should be under damping.
So it's the Lorentz force that causes the Lorentz force causes the damping effect.
So if you can plot a graph to summarize your problem, experiment, theory, so what would you do?
If I could.
Since there is no graphs.
Oh,
No, not many graphs.
well, it would be more clearly that like how the Lorentz law, the Lorentz force impact the whole damping system, which I could possibly like put it all on the same graph, and we could first we could observe the period, and we could observe the decrease of the amplitude.
Okay. So will the wires kappa get the results?
Which kappa are you
The wire.
What is
Sorry,
oh,
time's up. Reviewer, please take the floor.
Okay, so thank you, the recorder and the opponent. So I'm the reviewer of Team Cypress, and today going to do problem number 2, oscillating sphere. So this is a problem statement with the classification. So this is the pros and cons. So for the reporter, the pros is that there is well explanation of the experiment step and well theory. But the cons is that lack discussion of the theory with the experiment, since there's not many clearly experiments set up, and there is no correlated comparison. And for the opponent, the pros is that the opponent just asks direct questions, and he's got a great schematic of eddy currents and just indicates the phenomenon very clear. But the cons is that the opponent just used too many theory that didn't mention in his presentation. Okay, so this is a PF question. So the opponent question is that why is the sphere without magnetic field oscillating? And so why is the sphere damping without any current? So and the reporter says air resistance in the wire, and which we think the reporter is right. And so just how did you define that the phenomenon will happen? And the reporter says he compared the results without magnetic field. So, and we think the reporter just stated clearly, but maybe he can give more quantitatively comparison. And so, and the opponent just asked the Lorentz force or torsion, does it affect the motion? And the reporter answered, we just can't record this one. So the opponent just asks what is the conductivity you use. Okay, so the opponent just asks is the Lorentz force the main cause of the damping, and the reporter says yes, it's the main cause. And we agree with the reporter since the other damping one. And the opponent just asks why there are some deviation in the chart. And the reporter says because we do many times of experiment. So I think that do many times of experiment is great, but you should just not considering the one with too many deviation. And time for reviewer question. So what is the main parameters to cause the motion? And the opponent says about the Lorentz force, and the force is about the Lorentz force and the sphere, and which means the reporter's answer is more precise. And the reviewer just asks whether the sphere you use how will affect or not the result. And the opponent said that both said no. So if you can plot a graph to summarize your experiment, what will you do? Then the reporter just says to summarize the data and you predict together and just get a plot, which we think that still needs more explanation. So the last one, what kind of damping it is?
Yeah. Sorry, time's up. So concluding remarks of the reporter.
Sorry about that. First, appreciate the effort from both reviewer and the opponent. And here's my concluding remarks. So firstly, I should have included the error bars since what both the opponent and the reviewer have mentioned. And of course, more careful experiment setup that I should conduct it in the whole experiment to ensure that there's no too much deviation in the whole process. And thanks for these suggestions from the opponent that I should have considered the air friction and the torsion damping into consideration when modeling the theory. And of course, should include more detailed diagrams, and also appreciate for the opponent's help for explaining how the Lorentz law affects the whole motion, like how the Lorentz force affects the whole motion. And well, I just like to use the time to clarify the graph that I mentioned here. Is that I used the condition that I didn't put in any electricity as the base of the A/1, and I minus it every, like for example this one, the 2.808, and I minus it for the base 2.306, and which that is the dot on like the dash one. And what I was trying to prove is the theory here, which is square root for respect of the magnetic flux density. So that will be my end of concluding remarks. Thank you.
Okay. Questions from the jury?
Question for all three of you. What initiated the oscillation? And why?
Could you restate the problem?
What initiated the oscillation of the sphere, and why?
Starts from my hand. So that is not a quite stable part. So first of all, I would give the sphere an initial angle, and then release it. So the torsion from the wire would like turn the sphere back, and which starts the whole motion.
So where is the oscillation?
The oscillation is for the angle, like yeah, you got the ball right. Can you like? Oh, thank you. Well, so just for example, the ball is starting like this, and I give it an initial angle here.
Yeah.
So if I follow the dot here, it would go back and forth, back and forth, back and forth, and then like decreasing the amplitude of like the motion here. So I use the graph the time to the angular displacement on the ball, which is actually more precise to see from top of the ball, which I can see the red point swings from here to here, back and forth, back and forth, back and forth. And this is what the oscillation means in the whole problem.
Okay. How about you?
Okay, so I partially agree with the reporter. So it does not oscillate itself. In fact, you need to give a releasing angle, or so that it has angle displacement, so that it tries to restore back to the equilibrium position. However, it will not stop in here because that it has angular velocity, and therefore it starts to oscillate. And the magnetic field inside this problem statement is actually causing a damping effect to prevent it from oscillating. And so therefore it's actually has a damping effect, so the oscillation motion will not be that significant after the time.
How about the reviewer? Briefly just get it initial torsion.
So, other questions? Jury?
No, it's time to prepare ranking.
Okay, so first for reporter, 7, 7, 5, 6, 6. For opponent, 8, 7, 7, 7, 7. And reviewer, 6, 6, 5, 5, 5. Okay, so any comment on the jury? General comment? Okay, the session is over. Okay, thank you.